Hi there. Today we're looking at Dream to Control Learning Behaviors by Latent Imagination by Danijar Hafner, Timothy Lillikrap, Jimmy Ba, and Mohammad Norozi. This is a reinforcement learning paper that iterates on a kind of a series of previous papers where the goal is to learn a policy. In this case, they want to learn policies for these kind of continuous control tasks. So these physics-based robots, these hopper or walker types of tasks where you have to control this robot, these joints, in order to move forward. And so the goal is that you have multiple observations, as you do in reinforcement learning. And from each observation, you need to somehow come up with an action of what to do. And then that will give you the next observation as well as a reward. A reward for, if your goal is to move this spider, maybe the reward is proportional to how far you move. So your goal is to collect the maximum reward, which would mean you have to move the spider as far as possible, simply by doing the correct actions. The goal of this paper now is to do this by learning to sort of plan ahead in this latent space. So as you can see here, the way they do it is they take the observation and they feed it through an encoder. Now you can think of this as maybe a convolutional neural network or something, anything that can work, that can take an image as an input and give you a hidden representation. So now this here is the hidden representation. From this hidden representation, you can determine what the next action is going to be. And then you get a new observation, and then again you can feed that along with the last hidden state into a new hidden state. So this is already previous models do this a lot, right? You encode your observation and you have a sort of let's say a recurrent neural network that incorporates all of the observations into a hidden state along with the actions you take, and then you always decide on a next action to do. So what does this model do differently? This model wants to do this all in hidden space. So what this model wants to do is it wants to say, okay, I am here, I have this observation. Now my encoder tells me that this is going to give me this hidden state. And now what it wants to do is it wants to take in the action that it's doing, and without seeing the next observation, right, it wants to predict it, right? It wants to say, well, if I am here and I do this action, what might the action be? The action might be to put the joystick to the right. It will learn the hidden state corresponding to the spider being a bit more to the right, right? So this is a bit more to the right than it is right now. And it will do so a number of time steps into the future. And it will kind of learn from its own imagination. So this is what it will imagine into the future how the hidden states look. And then it will learn from that instead of having to really do the actions in the real world. Now, we've already looked at a number of papers, including something like mu0 or I2A or something like this. This now is slightly different. So you can see, so what's different here? What is different is in mu0 we had this, we used this latent model in order to plan ahead, like in order to do our decision tree planning ahead and so on. This model doesn't do this. This model still wants to come up with a single policy where you encode your state, right? This is on the right is the final result. You encode your state, gets you to a hidden representation, and then from that you determine what your action is going to be. And you have your next state, and so on. So the final goal is simply going to be a policy, like a single shot policy without any Monte Carlo tree expansion and so on. But what it wants to do is it wants to learn this policy, not by interacting in the real world, like here on the left, but actually by interacting only in the dream world right here. So the crucial part, if you want to learn from your dreams, right, is to make sure that your dreams are an accurate representation of the real world, right? We already saw this in a paper called World Models by Jürgen Schmidhuber, I believe. And in that paper, what they did was they first collected experience, such like experience like this one, and then they learned from the one observation to predict the next ones, or to predict the next hidden states, right? They did so by basically moving in the world at random. So they have this little spider thingy, and they just do random movements, right? They randomly move around, and thus they collect these trajectories, and then they learn from the random trajectories. The difference that this paper does is it does these steps iteratively. So it will not learn from random policy, but it will actually first, it'll start out learning this random, learning a good policy for its environment model, then going back and using that policy in order to learn a better environment model, and then again using the better environment model in order to learn a better policy. If this wasn't clear enough, we'll jump to the algorithm. The algorithm isn't actually too complicated. It's, as I said, I think it's a relatively minor iteration on previous research, but it appears to work, and it works in these kind of continuous control tasks. So you see you have 3 models here that you need to learn, and that's what you see over here. There is representation, transition, and reward, and you'll see they all have the same parameters. So that gives you an indication that these things are a single model. Now, what is the model? Representation, transition, and reward. So let me. This is the thing on the left here. In this part of the algorithm, you assume that you have a policy. You already know what action you do. Or you can even assume that you have some experience, right? Your agent is running with a given policy, and you simply collect that. And now you're trying to learn. So let me scratch all of this. What do you have given? Given is the observation sequence and the actions you took, right? And the rewards you got. That's also given. So each action gives you reward, right? So these things are given, provided to you. And now what do you want to learn? You want to learn a representation and a transition and, let's say, a reward. So you also want to predict the next reward. This thing, right? So as we already said, you can do this by encoding the state using, for example, a CNN, and then using an LSTM in order to incorporate this over time. So what you learn is the transition from one hidden state to the next hidden state, and you also learn how the observation goes into the hidden state. And thirdly, you learn that if I'm in this hidden state and I take this particular action, I will get this reward in the future. Right? You can learn this from just a set of pre-computed, or from a set of experience that you have in your, let's say, your replay buffer. Right? This is one model. And you learn this here in this first step, in this called dynamics learning section. Right? So you see, while not converged, so you do dynamics learning. You draw data sequences from your experience, right? Then you compute the model states. These are the hidden states. And then you update this parameter theta using representation learning. Now, they don't really specify what representation learning is, but they do give examples of what you can do. I think their point is whatever you need to do in order to learn this representation. And one example is actually drawn here. One example is you can learn a model that reconstructs the next state. Reconstructs the same state. So you can learn a model that predicts, so if you give the observation as an input, it goes through the hidden state. You can learn a decoder that reconstructs that observation. This is usually done in things like variational autoencoders in order to produce generative models. So the this part here would be the generator, and that would be kind of the thing of interest if you are doing a variational autoencoder. But of course here, our quantity of interest is this encoder model, because we want a good representation of the state. And but it comes down to the same thing. If you can learn a model that learns to accurately reconstruct the observation, then your representation here in the middle is probably an informative one, right? Because you learn the same model across multiple observations. That means it can accurately encode what makes one observation different from another one. Right, so this is how you learn the theta parameters, right? Now, the other models here are the action and the value parameters. And this is here in the step called behavior learning. So in the behavior learning, what they say is imagine trajectories from each of the states that you have. So what you're going to do is, from each of the observations here, you're going to obtain the hidden states, right? These hidden states. Now, from each of the hidden states here, so here is an observation. From its hidden state, you're going to use the model that you learned here through the LSTM. Sorry. Well, this is terrible. Through the LSTM, you're going to use that model to imagine future trajectories, right, of hidden states. So you have given R now is the observation here and the hidden state, and you're going to imagine future hidden states. You're also going to imagine future rewards, right? And you are going to use your policy kind of to you're going to use your policy in order to determine which actions you're going to take, right? And the ultimate goal here is to learn a good policy, so a policy that will give you better rewards in the future, as you would do. So this is regular reinforcement learning, except that the difference is, in regular reinforcement learning, I have my observation, I encode it, and then I determine what action I want to take. Then I feed that action back into the environment, which would give me the next observation, and then I'd use that to determine, maybe in conjunction with the last hidden state, the next action. In this thing, since we learned a dynamics model of the hidden states, we can simply determine the action and then simply compute what the probable next hidden state is going to be, and then use that to determine an action again, and so on. So there's no need to go through the environment, which means potentially we can learn much, much faster without having to expensively interact with the environment. And that allows us to basically, also these models here, they might be quite large. So our backprop now only needs to happen through this path, basically, if we want to. Or through this path here, in case we have discrete actions. Yes, so that will be the dynamics learning. This is down here. Alright, so you can see we predict the rewards and the values and compute value estimates, and then we update these parameters using. So what we have is here a value function. See, the value function is dependent on this psi here, and this we update using a gradient of its output minus the true value. So this here is an estimate of the value, and as you know, a value function is supposed to tell you the complete future reward given a state, right? And it's important for us that we have a function that can estimate that, because of course then we can take actions if we can make this function go high, and this is an accurate function. That means we get a lot of reward in the future, right? So it's important to learn this function, and here you can see we adjust it into the direction of matching this quantity better. Now we'll get to this quantity in a second. You can also see we update this parameter, which is the action model. So here you see that the action model depends on this. This is our policy, right? This thing here determines which action we take, and we update it into the direction, this is a gradient, with respect to this value function, right? So we train the policy to maximize the value, which is all the future rewards that we get. Of course, we can do this because we can now back propagate through all of these time steps, because we have this transition model. We can back propagate through all of this, which is pretty cool. I think, in my opinion, the kind of workhorse of this paper might be this quantity here. So how exactly do you compute the value of a state? Especially in these continuous control tasks, you sometimes have a lot of steps. So these trajectories might be pretty long, and they might be longer than what you can back propagate here reasonably from time step to time step, right? Even an LSTM might only be able to backprop through, let's say, a couple of dozen or maybe a few hundred steps in time, and maybe you have longer trajectories here. So it's pretty, I think this value estimate here is a main component of extending that range. So they say this is according to equation 6, and this is what it does. Again, this is my opinion that this here is kind of the workhorse of the method. So it's a 3-step process actually. It's pretty heavy. So you see, this is the quantity they estimate with the value function. It is set between an average over, so h is the time horizon, right, that you're looking for. It is set between these two things across the sum over the time horizon. Now each of those things, again, here is a sum over this tau here, which is this tau, and the h minus 1. And h here is the minimum of tau plus k and tau plus horizon. So this quantity looks k steps into the future. So for each step to the horizon, we look k steps into the future, and for each step we look into the future, we sum again across these quantities here. And these quantities here, what is that? It's a mixture of the reward you get in that particular step plus your estimate of the value function at the horizon step, discounted by that. So it's so if you imagine you have like a time number of steps that you took, and each time you get a reward, right? This is a very complicated way of going into the future, summing up the rewards, going more steps, summing up the rewards again in different fashion, and then mixing these individual quantities. So this one that you got from accumulating all of these in a weird fashion. And that allows you to look way beyond. Especially, you see here, your estimate of the value function will actually include your own value function that, again, probably looks into the future. So what you accumulate from the last step in your time horizon already includes information from all the future steps, because you take your own value estimate into account. This is, I think, it's very convoluted, but I think this complicated value estimate allows you to have a better value estimate far into the future. They do show some kind of samples here of what they can do. I haven't found any videos of it, unfortunately, but it appears to work pretty well. They have a discussion of different representation learning methods and different experiments and ablations and so on. So I invite you to look at this paper, and I hope this was somewhat clear. Bye-bye.